We have heard that some companies are resilient. But what does it mean to build resilience? Also, are bad designs the only reason behind human errors? And what's the deal with Swiss cheese and product designs? Hello, and welcome to a brand new episode of Mind Brunch. Let us look for answers in the final part of the series on Design for Error. If you have followed this series from the beginning, you would have understood a basic premise with errors. Not all errors lead to accidents, although very few among them have the ability to individually cause large-scale catastrophes. But, in a majority of these cases, it is these small errors that aggregate to cause major accidents. An important aspect of errors leading to accidents is that many errors are interconnected and can be traced through one another. So what's this got to do with Swiss cheese? The answer lies in the cheese itself. James Reason explains the compounding of errors by using the metaphor of Swiss cheese. This variety of cheese is visually identifiable with the presence of numerous holes. Imagine a big block of Swiss cheese that is being sliced. You want to now undo the task and want to put them back together. Your job is simplified by the nature of the cheese itself. All you have to do is line the slices by matching the holes. This is how you can attempt to recreate the block of cheese as close to the original as possible. And rebuilding blocks of cheese from the slices holds an important lesson in understanding errors. Oftentimes, an investigation team tries to single out a cause, one particular misstep, that could have caused the entire ordeal. If we know anything about such investigations, it usually ends up being a human element. However, with an approach influenced by the hole-ridden Swiss cheese, investigators can commit to having a more systemic view of a disaster, by piecing together all the errors and interconnecting them. Such an approach has a two-pronged outcome. On one hand, we can finally expect all the causes to be outlined properly, and can retrace the run-in to the eventual accident. Along with this, we will be able to identify weak areas that tend to contribute more towards an error, and redesign them effectively. As a bonus, this approach also leads the investigators to identify the critical chain of errors that cause the most damage, instead of identifying every few interconnected errors as guilty. Some errors just don't affect the system. So what does the Swiss cheese model have to teach designers? Add more slices of cheese, meaning they should design such that only if a lot of errors occur in a particular order, the product fails. Decrease the spaces, or make them smaller. This implies that the designers have to reduce the paths for errors to influence each other, and also make the probability for an error to make an impact on the system less. Alert the operators when a lot of spaces, that is errors, line up. Now, with all the design principles having been implemented, what might be the reason if some errors continue to occur? Then they must be exclusively human errors after all. One cannot blame the design of the cockpit for an accident if the pilot operating it was sleep-deprived in the first place. There are situations when the blame falls squarely on a human error, and rightly so. We wouldn't want to undergo a tricky surgery if the physician hasn't taken a break for a long time and is most probably working under fatigue. Or how about taking a bus ride where the driver has been so busy that he hasn't eaten anything and expectedly has low glucose levels? There are many tasks which require a skilled person to be at the helm. As seen during the discussion of a company-wide culture of rewarding risks, some people continue to work in a less than optimal mental or physical state if it means that they can complete a task and be rewarded for the same. Even when an operator is in the best physical shape and mental state, there is still room for errors. Slips basically occur with experts, as we had seen. So there's always an odd chance that the most experienced pilot reads the warning wrong. Sadly though, such rare occurrences still translate to quite a number of accidents in the real world. Let us assume that industrial facilities have already executed the design changes and employ state-of-the-art warning systems. Suddenly, they are hit with an earthquake, a tsunami, or some other unexpected natural event. Here, the cause of a probable disaster lies outside of the controllable system. It is for such situations that resilience needs to be developed. The aim is to continuously assess, test, and improve responses to a continuously changing event. The same needs to be built in product designs, warning systems, safety procedures, and mainly, communication protocols between workers. While basic computer-based simulations might provide very little insight into how systems react under massive unexpected stress, it is only possible to study the same by conducting a full-blown mock drill. Computer systems used in information security and data handling are subjected to extreme tests and attacks to test the ability of the system to sustain and work within acceptable limits. Resilience engineering is best described as a step in safety management that focuses on the aspect of helping people cope with complexity under pressure in order to succeed. Thus, a resilient organization shall treat safety as a core value and not merely as an optional commodity. Let us turn our focus to the one thing that seems to be the answer to everything these days. Automation works wonders in many situations. Smart systems, across the world, employ automation to ease the responsibility on humans, and thereby, eliminate errors to a great extent. Self-driving cars promise to reduce accidents to near-zero levels. Automatic electrical grid management proves its worth by ensuring swift handling of variations in loads. They are used in grids which draw power from different sources and distribute in an optimal manner. However, there's a flip side to even the most noble of things. And automation cannot escape this principle. Automation can replace human work that mostly involves menial, basic, straightforward tasks, even if it involves high-level calculations. Complex tasks are not easy to automate. Hence, in the event that they are faced with a complex dynamic system, the latter can push an automated product to its limits, even confusing it to committing an error, something that it was built to overcome. Also, when an automatic system gives way, it can do so without prior indication. This means that the people associated intricately with the management of such systems can be left outside of the feedback loop, which is critical for error detection. There have been recorded examples of how automatic GPS systems have led ships to sail hundreds of miles away from the intended destination. This happened once, as the GPS system was disconnected from the antenna and had to depend solely on the approximate position of the ship, its speed, a sense of direction it was aligned to, and make a critical guesswork regarding where it was required to reach. Moreover, the captain was unaware of a tiny aberration in the display, which was meant to indicate this particular malfunctioning of the GPS system. What could have possibly gone wrong? In the end, let us summarize all that we have learned in this series. A properly designed product recognizes the places for error creation and seeks to actively suppress or completely eliminate the same. Here are the important principles that one needs to remember while designing systems. Have the complete information about the tasks in public knowledge. This not only helps novices handle tasks with confidence, but also helps experts tackle tricky unfamiliar events. Include natural and artificial constraints. Harness the power of influencing certain habits and evolving mental mappings through physical, logical, semantic, or cultural boundaries. Connect the far-off worlds of execution and evaluation by providing enough clarity. During execution, provide sufficient options, as well as feed-forward information. On the evaluation side, provide feedback, thus making the outcome of actions known. Make it easier to determine the present status of a system, with the critical information presented in a way that is easy to identify and understand, thereby ensuring that the actions are in line with the intended goals. This was the sixth and the final part of the series on Design for Error. The main source is the book, The Design of Everyday Things, by Don Norman. You can find the link to purchase the book in the description, down below. What is your understanding of human errors, now that you have a whole new perspective of them? Share them in the comments section. Give this video a thumbs up if you learned something new, and share. Also, subscribe to the channel if you haven't. Thank you for watching this episode of Mind Brunch.